So, friends, welcome to the third lecture on calculus of more than one variables. You see the heading today, application to real world problems. Also here I am written on the screen, application to real world problems. You must be thinking that I must be talking about something very important, very realistic, take some real problem and try to solve it with whatever little we have learned. No, the idea is no, and hence this name could as well as be thought as a misnomer. It is to tell you that real world problems are very tough. It needs a lot of people to come together, and then keeping and taking various aspects from various fields, one has to really handle a real world problem. But there are certain tools which are required to solve real world problems. Some tools of natural science like physics, and mathematics is the way where these rules of physics or natural science is described. So, here we are going to be concentrating ourselves on the use of vectors in physics. And you can see this can be done with whatever knowledge we have already got about vectors, about say we have learned about inner products. See, the idea is to show you with that this little knowledge that we have gathered over the last two classes can be sufficient to understand some bit of what I call classical mechanics or Newtonian mechanics. Newton was of course the most famous genius you know, other than Albert Einstein. Newton was born in 1727 in England and went on to become one of the greatest scientists who ever lived. In 1687 he published a book called Principia, which is in short called Principia or Newton's Principia. There he actually laid out in mathematical fashion the laws of motion, or he studies the properties of moving bodies. So, mechanics is about the study of moving bodies. Mechanics studies bodies in motion. So, this is what you have also learnt a bit in your higher secondary classes, or maybe even learning in your first year classes in physics. So, that is why relating things to mechanics would make life much more easier. In mechanics, we are often talking about point particles. I would again say that Newton's mechanics talks about motion of bodies around us, which we can see. It does not talk about things at the atomic level. Things at the atomic level does not conform to Newton's mechanics. So, and you will see the introduction of this term point particles in most books of mechanics. And I want to really tell all of the students who are watching this, you should go and read the preface of the Principia. and then you can understand the clarity of Newton's mind, where he essentially tells you that you see in geometry, he was interested in geometry, Euclid's geometry. He said that we learn to draw circles, we learn to draw ellipse, we learn to draw several curves, parabola, hyperbola, but how does nature draw them? So, if for example, the sun is having a gravitational attraction on the earth, then how is the earth supposed to move around the sun? It is supposed to move around in an ellipse. So, nature has a mechanism to draw those curves. So, in that sense he puts geometry even as a part of mechanics, but he also says that the mechanics that he talks about is not really the mechanics of doing nuts and bolts, but mechanics which is a mathematical modeling of nature. So, here is this important term that comes in, is the mathematical modeling of nature. Mathematical modeling of nature. Those who would be physicists, those who would be applied mathematicians, those who would be engineers, they should get habituated with this term called mathematical modeling of nature. Mathematical modeling, that is modeling real world problems in a mathematical format, is not an exact description of what is happening in nature, because exact description is very complex. Too many complex things happen for us to really fathom, our brains to really fathom. So, what we do we take very simpler situations in which we can use mathematics to describe them, and describe them through some equations, solve those equations, and then try to interpret that phenomena. So, what we do is not exact. So, a large amount of exact science depends on non-exact things, or on approximation. So, approximation is the key issue in science. So, you have to carry on your scientific career or engineering career by understanding the role of approximations. Approximations play a key role in science, so never ever forget this. So, what is a point particle? So, you can say, okay, a ball rolling past me, is it a point particle? I can see the object. But if you are, for example, looking at the planetary system, then compared to the sun, for example, compared to the sun, a planet moving around the sun, compared to the mass of the sun, a planet can be thought of as a particle. So, here is the sun and here is the planet. In fact, if you are looking at an apple falling from a tree on the earth, that is what Newton had been famous for. So, here an apple is falling. So, compared to the mass of the earth, the apple can be viewed as a point particle. That is, all its mass, or you can say, okay, point by geometry means it has no dimension, it is just a kind of very idealistic thing. It has essentially a thing which I cannot think materially exists, I agree, but the whole point is that we are thinking, there is no harm to think, and that is what science is all about, to imagine that this apple that you are thinking about can be viewed as something which is so small compared to the earth, that it is so tiny that it looks like a point, and the whole mass is concentrated here. So, many of you might have heard about the term center of mass when you study mechanics. The center of mass actually gives justification to this idea that if you have a system of particles or even a rigid body, you can define in terms of other particles a point where all the mass of the body would seem to be concentrated, and that point particle can be thought as a representation of the body itself, and that is why it does not harm to talk about point particles. So, what should I know about a particle? Classical mechanics is about predictability. or Newtonian classical mechanics is another name of Newtonian mechanics. So, I just get you habituated with the names, is about predictability. It means that if I know the current state of a body, so what I mean by the current state of a body or state of a point particle. So, we will tell you what is it. So, if I know the current state of a particle, I can tell how the particle will evolve in the future and how it has evolved before. So, it is a completely predictable system where no uncertainty is involved. So, Newtonian mechanics is a system where there is no uncertainty as far as so this is something which is very important to understand. So, what is the state of a particle? Any particle that is moving say in space changes its position with respect to time. So, once you are talking about real world problems here, let me tell you Newtonian mechanics still continues to be applied in many cases including space explorations and all. So, let me tell you that this a point particle P, you see the position of the point particle. This point particle as it moves along a curve in 3 space, it changes its position in time. So, at time t1 it is here, which I call p1, at time t2 it is here. So, here its position is given by a radius vector r_t1 and here its position is given by the radius vector r_t2. Obviously, here r_t1. So, in general the position of a particle is given by the 3 coordinates which also depend on time, as time, because the body is moving at as time evolves, the body's position keeps on changing because it is moving just like a moving train. Right? And then you need to know what happens is that we are not just in what is the meaning of a state. State means where is it at a given point of time and how fast the body is moving. So, both information are important to know about the future and also know something about the past of the body of the particle. So, we also have to know the velocity of the particle. So, what is velocity? Velocity is nothing but the time derivative of the vector r_t. So, which we can now write as r dot t, which is the vector x dot t, y dot t, z dot t. Of course, you can write, it is no harm to write this r dot t as or r_t whatever as x dot t I vector plus y dot t j vector plus z dot t k vector. Now, a state of a particle then is really governed by these 6 elements. So, state of a particle, you see how we are using our simple vector ideas to define things. So, we are talking about physics of mechanics and we are talking about this. So, state of a particle is actually defined by a 6 dimensional vector. So, a vector is not just 3 dimensional or 2 dimensional as we have been studying, it can be more than that. That is, we will also talk about n dimensional vectors, that is pretty large. So, here we need a 6 dimensional vector to define what is called a state. So, suppose you have two vehicles A and B, they are moving, right, and with respect to some origin, the position vector of the vehicle A is described by RAT and the position vector of the vehicle B is described by RBT. Then this vector which joins B with A, which you know from very basic vector geometry, is RAT minus RBT. Then the vector, this vector which we call RAB is a relative position of A with respect to B is given by the vector RAT minus RBT. So, this is the relative position of A with respect to B. I know for many of you must have worried about the concept of relative velocity. Relative velocity of one body with respect to the other. So, if this is a body moving in this direction, a ship moving in this direction, then there is another ship moving in this direction. So, what is the relative velocity of A with respect to B? So, what does it mean? I am now on the ship B, and if I think that my ship B is at rest, what is the what velocity and in which direction I see the ship A moving? I know my ship B is moving too, but I am on it and I want to make it as if that the ship B is rest, thinking that the ship B is at rest, I want to see in the water, in the sea or river, whatever, in which direction and at what velocity the ship A that you see here actually moves. So, to really think that this ship B is at in a stationary position, it has halted, then you really have to. So, if this was moving with a velocity Vb and this was moving with a velocity Va, to stop the ship B you have to apply an opposite velocity, so that the total velocity of the ship B is 0. And then what you really have to do is, now once you do this, it is 0. Now, with respect to this ship, how will this be? How will this look like? So, basically you add this velocity with this velocity. So, basically I am telling, okay, if I apply minus Vb velocity to the ship B, my ship B has stopped. Now, my ship A would actually look to move in this direction, which is Va minus Vb. These are all vectors, of course. And you see, this is exactly the vector Va minus Vb. That is exactly what is the meaning of relative velocity. So, it is nothing but the time derivative of the relative position. So, basically what it says here, What is the meaning? This is a very important thing. What is the meaning of relative position? If the origin was O, then the relative positions of A and B, the positions of relative positions of A with respect to O is RA, with respect to relative position of B with respect to O is RB. But then if B becomes the origin, then what is the position of A with respect to B, and that position is RAB. So the whole idea is making B the origin. So when you are talking about this relative velocity, the whole idea is about making V the origin. So if I make V the origin, this is my V, V has now halted, and now if V is the origin, how do I look at my ship A, in which direction the ship A is? If V is the origin, then the direction in which my ship is this, and hence it must be moving along this direction, which is exactly VA minus BV. So what is relative velocity? So again, relative velocity is the time derivative of the relative position. That's it, as simple as that. So what happens, what is the velocity of the ship A when my origin is now thought to be B and not O? That is the whole idea. So it is a time derivative, actually with T I should write a T here, but you can fill that little error up, it is a little fun to say that the instructor is goofing up. Sometimes old men goof up. So now, so this you see, whatever little we know, we have really made an application. Now comes the idea of a force. Force is fundamental to Newton's mechanics, and everybody of you know, without, I am sure everybody sitting in this audience would know this famous law, which I am writing in the board in a very big way. F, the force, is mass times the acceleration. This is Newton's second law, or key to the universe, I guess. Because of the popularity of this popular science literature, this might be only second to E equal to mc square if you really take up the popularity of equations that is known to general public, but this is the key to the Newtonian heaven, right. And what is this force? How do I write it? How do I mathematically express it? Let me tell you, force, suppose here is a particle moving, here is this P, and a force is acting on it, right. Now this force that is acting on it is also a vector, and it will change in general with the change of the position. Now the force is itself a vector because it acts in all the three directions, right. It will, a force on the body is not only acting in one direction, but you can resolve it into three different directions. So the force actually has three components. So I can write it as force of x, y, z. Obviously these x, y, z are also functions of t. So at the end everything becomes a function of time, but we did not put time explicitly, hoping that you understand whatever happens in mechanics or in dynamics, because things are moving, has to depend on time. So this f of x, y, z has three components. One component in the x direction, so these are scalar quantities, another in the y direction, another in the z direction. That is, my force can also be written as F1 I vector plus F2 j vector, they are the coordinates of the force. So, the force vector F is acting on this particle, F is acting, right. Now, what are the coordinates of this force vector? So, that is about it. Okay. Now, how do you express this thing in Newton's law? So, acceleration can also be expressed, this A vector, which is actually a function of time, can be also expressed as a time derivative of the second time derivative of the RT vector, that is the position vector, because the velocity is nothing but r dot t, and so acceleration is again taking nothing but again taking the time derivative of the velocity. So, it is, so from a vectorial way, Newton's law can be put in a very simple format, that is m, and so this is not a velocity. See, when we largely study particles moving in a straight line, but when you have particles moving in 3 space, this is the way to very compactly you write down your Newton's second law. Please understand that this is actually 3 equations combined into one. That is the beauty of a vector expression, that it compresses a lot of equations into one, right. So, this is the Newton's second law. The key to the universe actually. Okay. Now, for example, let us take the book which I have been working on, or let me just take a problem from the book. And try to see what happens. Let us try to do some exercises here. So, suppose there is a, I am doing a problem, right. This time let me just concentrate on a problem. Suppose there is a wind velocity of 40 miles per hour, and this is a British way of speaking, miles per hour and all are, you do not hear, or I mean, or you want to say 400 kilometers per hour, whatever. So, there is a wind velocity. So, wind is moving from east to west at 40 miles per hour. So, this is what we call V1, and a plane is moving in the northerly direction. So, this is the north at 100 miles per hour, which is very slow actually for a plane. These are speed of a train nowadays in most countries. So, this is V2. So, in which direction the plane, from the ground I see the plane actually starts moving northward, but from the ground in which direction do I see the plane moving? So, here what happens is, here is the plane moving straight upwards, here is the velocity which tends to push the plane towards the west. So, basically the plane would now move at, to me it will appear in the ground as if the plane is moving in a slightly westward direction, northwestwardly direction, which is given by the vector V1, V2, okay, V1 plus V2. So, this is an application of that ideas that we are saying. So, you can easily figure out what is this vector V1 plus V2. So, V1 is the, So, V1 plus V2, the square of this by law of Pythagoras is V1 square plus. So, let me don't V2 is like V1 and V2 are these are magnitudes of the vector V1 and V2. So, V1 is the velocity here. So, the direction is east to west and here is towards north. So, from the airport it is I am observing that it is going up in the sky in the north, it is going up in the north actually, but from the ground I am observing as if the wind is pushing the plane towards the west. So, by Pythagoras theorem I will know what is the magnitude of the velocity. So, magnitude of the velocity, sometimes I can write just this as V1 square because this is just a real number. Pythagoras theorem, just apply it here. I do not want to go into teaching you what is Pythagoras theorem. So, you can just apply it. So, so immediately you know what is this 40 square plus 100 square. So, that is what you have 40 into 40 is 1600 plus 100 square 10 plus 10,000 10 to the power 4. So, I am so bad at doing these computations. So, 11600, so bad. So, now V1 plus V2, the modulus, the actually the velocity with which the plane is going to move is I am observing the plane as if it is moving now at a velocity of root over this miles per hour. So, here is a demonstration of what we have just learned which can be applied. Another demonstration comes to work done by a force. And you will see how inner product comes into play. So, what is work done by a force? I will just remove it here and just try to explain it to you here what is work done by a force, and then we get into the vectorial form of it. So, there is a block of wood here and there this is a very smooth table. I am ignoring the frictional force that there will be, but I am giving a force F, I am pushing it and I am starting say from here where the center of mass is, say the point A, and I am moving this finally the body to point B, that is the center of mass comes to the point B. I am not getting into the discussion of center of mass. If you want to look in, just Google it, Wikipedia would have it surely. So, this distance that I have moved this body, basically the point particle which is the center of mass, if I call it S, then the work done is force into the distance. So, magnitude of the force. So, work done is actually a scalar. So, magnitude of the force into the distance. So, I am not writing F, F simply means the magnitude, that is what is work done. But suppose, so into the distance is S here, sorry I have said S. So, it is S. Now, suppose there is a big boulder, a rock, and I am trying to push it with all my strength, then it does not move, whatever force I am applying it does not move, then my work done is 0. For a work to be actually done by a force, the body needs to move a certain distance. But what happens when I am in this setting of, let me draw the axis first. The best thing in this is to draw the axis first. I am not so habituated handling this electronic pen, so you forgive me for this. You can definitely draw better than me. Now, suppose the body was moving and it has gone from P1 under the action of a force F to P2, and let me assume that the force is constant. So, for every position r at every time t, the same force is being applied on the body. So, F r is a constant vector, is constant. So, now suppose this is r P1 is my position vector of P1 and r P2 is my position vector of P2. Now, you might ask me that what happens if I go through a curve, then how do I really handle the situation? How do I really calculate the distance? Okay, here is a crux which we cannot come in now, because this will lead us to something called the line integral. We will discuss it later on, and then work will be discussed in a much detailed way. Let us assume that this has moved in a straight line between P1 and P2. Then the distance covered between P1 and P2, so the distance covered under the force, distance covered is Rp2 minus Rp1. So, now this force F was acting on it constantly. So, how do I define the work done? So, work is nothing but multiplying, we define work as multiplying the force with the distance, but here you are in 3 dimensions, you know, and you know when you are in more than 1 dimension, 3 dimension, what is the generalization of multiplication, what is the way we generalize multiplication of 2 numbers into multiplication of 2 vectors. The way we know it till now is called the dot product or the inner product. So, work done, which is W, is given as W is equal to F dot product Rp1 minus Rp2 minus Rp1. So, you see the things that we have learned, the little things that we have learned in the 2 classes have actual applications, have actual meaning, can be really used to talk about something meaningful, talk about something practical, talk about something that we want to see and we want to discuss. So, here is a gamut of things that we have done. I guess that with all this you have some idea. Another thing that I want to tell you, for example, many of you know what is kinetic energy. Kinetic energy, you know, even if it is in 3 dimension, if body is of mass m, it is mass times square of the velocity. Now, when the body is actually in 3 dimensions, square of velocity means square of the magnitude of the velocity. So, half of m into x dot square, these are all functions of time by the way, y dot square plus z dot square. So, this is equal to half of m times, if you look at the notations, this is r dot inner dot product with r dot. So, you see the dot product is again used to describe kinetic energy. So, when we learn more about derivatives and gradients etc., we will see how this formulation would help you to very simply prove the fact that the total energy, which is a joint, which is the summing of the potential and kinetic energy, is independent of the time. That is, the time derivative of energy is 0, that the energy remains constant in time, and hence that is what we call the conservation law of energy. So, all these simple this sort of vectorial writings will help us do things much more simply and give a much more clarity to whatever we have already known about in physics, in mechanics. So, mechanics, the idea applications from mechanics would come on and off. Maybe you can say I have a personal liking for it, yeah I do, I agree that I do, but this is something very important because mechanics is a very fertile field where vectors can be applied. Of course, it can be applied in a more abstract sense in quantum mechanics, the science of understanding the atomic, the thing subatomic world, but that is what we are not going to discuss here. We are talking about very concrete 3-dimensional vectors most of the cases. So, with this I close the talk for this time, this class. The next class we are going to talk about simple facts, determinants and matrices, and determinants and matrices will become important as we move on, because determinant is a kind of tool which tells a lot about what a matrix, how a matrix behaves, and matrix is a kind of operator which is all over the place. And for example, when you talk about derivative of a vector function, we are talking about matrices. I want to bring your notice to this. I want to bring your notice to this force vector that I have written. So, what is a force vector? In fact, it is true even of velocity vectors. So, force vector, what does it means? So, it had x, y, z and there were 3 components F1, F2 and F3. So, here it is a function of several variables, but this function of several variables f is not carrying this element in R3 to an element in R, it is carrying an element on R3 to an element of R3. Such vectors, such functions are called vector valued functions of vectors, or rather vector valued functions of many variables. When you are going to talk about derivatives of such functions, derivatives of such functions will be matrices, the things which we will learn in the next class. So, thank you very much, thank you for your attention, hope you enjoyed this class. You can obviously put your queries and we will try to answer them. Thank you.